Okay, so we would be dealing with this function right here, which is r is equal to 4 cosine 3 theta. But we have a note here saying that we must express our solution in terms of radians. So meaning this theta right here must be in terms of radians. So from that, as you can see in this table right here, the value for our theta, once again, is to be in terms of radians. And this one right here is to be our 30-degree equivalent. So this is to be in sexagesimal units and these are to be in radians. So this is to be in 60 degrees, 90 degrees, 120 degrees, etc. up until you reach 360 degrees. Okay, so after that, the first thing that you would be doing, since our coordinates are in terms of radians, is to change the setting of your calculator to be in terms of radians. So looking at the calculator to your left, so let's say that you would be having a certain calculator similar to this one right here. Press shift, press mode, then press 4. And once that you have pressed 4 already, every time that you would be using any of these trigonometric functions right here, your calculator would see it as radians. So let's say that our sine pi over 2. So this is basically sine 90 degrees in terms of degrees. So this should be equal to 1. So equal sign. So as you can see, our answer here is to be 1. And let's see, you would be getting the value of sine 90. Sine 90 degrees should be equal to 1. But since this is to be in radians, once you would be clicking enter, this is not to be equal to 1. So if you want to solve for this one right here, and you mean that this value right here is to be in terms of degrees, so shift, mode, then change it to 3, which is in degrees. So 3. So from that, our sine 90 is now to be equal to 1. Okay, so reverting it back to radians, since we are to express our solution in radians, so shift, mode, then 4. So as you can see in this part right here, there is actually a letter R, signifying that our calculators are reading angles in terms of radians. Our function here is to be R is equal to 4 cosine 3 theta. So I would be typing that function in our calculator, which is 4 cosine 3x. So there, and pressing calc. So what is to be the value of your x? So when your x is equal to 0, your r is equal to 4. So this one right here is to be equal to 4. Then pressing calc once again. What if our x is to be pi over 6? So pi over 6. So our answer here is to be equal to 0. So this one is to be 0. And for pi over 3, so okay, so plotting these coordinates right here would give you this graph. So what is to be the value for your r when your theta is to be equal to 0? That is to be equal to 4, which is, well, this one right here. And what is to be the value of your r when your angle is to be pi over 6? That is to be equal to 0, which is this one right here, so 0. And plotting the rest of the data would give you this one right here as your graph. So there. So as you can see, we have a 3-petal flower. So this is now to be its graph. So once again, our main focus for this video is for us to determine the area bounded by this function right here, which is, well, this one right here in our polar graph. So this is our polar graph. So how can we solve for this area right here? In integral calculus, in order for us to solve for the area here, is for us to get the infinite summation of a differential area. And our differential area in this part right here is to be this one. So let's say that we would be having this line right here. I mean this part right here and this part right here. So this one right here is to be our differential area. And what is to be our differential area? So I would be enhancing this one right here for you to see it. So let's say that this is to be your graph, and in this graph right here, this is to be your curve. So the differential area that I have drawn earlier is to be this one right here. So let's say that this is to be it, and this is to be it. So once again, I have just zoomed this in for you to see it clearly. So it would be this one right here. And this one, since this one right here is to be given by the function r is equal to 4 cosine 3 theta. So this value right here is to be your value for your r. And this angle right here is to be your differential angle. Since your d theta right here is very small, we are to assume that this r right here is to be the same as this one right here. Though it may not be true, since as you can see, your graph is to be leaning in this point right here. We are to assume that this r right here is to be equal to this r right here because our d theta is to be very small. Okay, so from that, our differential area right here, since if this is to be your differential area, it is to be equal to the area of a sector. So this is to be the area for a sector. So having a little bit of a review from your solid mensuration. So the area for a circle is equal to pi r squared. And we can get the area of a sector using ratio and proportion. So the area of a circle divided by 360 degrees. So let's say that our angle is to be in terms of degrees. So this is to be equal to, so the area of a sector. So suppose that we would be having a certain circle right here. And of course, the circle is to be equal to 360 degrees. Thus, this one right here. And let's say that we want to get the area of a sector about this point. So let's say that this is the sector that we want to solve, and let's say that it would be having a certain angle theta. So we would just be dividing this by theta. And cross multiplying, you would be arriving at an equation of area of the sector is to be equal to the area of a circle times theta divided by 360 degrees. So from this, so area of the sector is to be equal to, so what is to be the area of a circle? That is to be pi r squared. So pi r squared theta divided by 360 degrees. So if your angle is to be in terms of degrees, this is to be the formula for your area of a sector. But what if that your angle is to be in radians, just like in our example? So our AC, or the area of a circle, is once again pi r squared. And AC, which is this one right here. So what is to be an angle of one full rotation in terms of radians? So that is to be 2 pi. So basically 2 pi is equal to 360 degrees. It's just in radians. So 2 pi radians. And this is to be equal to the area of a sector divided by theta. And make sure that this theta right here is to be in terms of radians. Okay, so from that, cross multiplying, so your area of a sector is to be equal to AC times theta divided by 2 pi. So from this, the area of the sector is to be equal to, what is to be the area of a circle? That is to be pi r squared theta divided by 2 pi. So from this, the area of a sector is now to be equal to, so pi would just cancel out, so r squared theta divided by 2. So if your angle is to be in terms of radians, you would be using this formula right here for the area of a sector. Okay, so going back to this one right here, since our d theta is to be the area of a sector, so our differential area right now is to be equal to r squared theta divided by 2. But since our theta here is to be a differential theta, our dA is equal to r squared d theta over 2. So that is to be the area of this one differential area right here. So as you can see guys, in this point right here, if we would be getting this area right here, it is also equal to this half of the area right here. So the total area, of this function is to be equal to this area right here. Let's say that this is to be area 1. Area 1 times, we have 6 parts. So 1, 2, 3, 4, 5, 6. So this is to be 1, 2, 3, 4, 5, 6. So that is to be 6 times area 1. So from that, if you already have this area 1 right here, just multiply it by 6 to get the area of the whole function. So okay, once again, our d, this one right here is to be equal to the integral of r squared d theta over 2. So this is to be our general formula in getting the area using polar coordinates. Okay, so for us to get area 1, so this is to be equal to the integral of r squared. And as you can see, we cannot integrate this right away. So our value here must be in terms of d theta. So from that, our r here is to be 4 cosine 3 theta. So that is to be 4 cosine 3 theta squared times d theta divided by 2. But as you can see, we don't have our limits yet. So what are to be our limits? So if we want to solve for this area right here only, which is area 1, our limits should be this angle right here, which is 0 degrees, 0 radians, so 0, up until this angle right here. This angle right here, which is this one right here, or pi over 6. So pi over 6. So pi over 6. So solving for this one right here would give you an answer of A1. Then just multiply it by 6 to get the total area of this function right here. Okay, so solving for this integration problem right here. So this is to be equal to, so the integral of 0 up until pi over 6 times, so what is to be this one right here? So that is to be 16 cosine squared 3 theta d theta over 2. So 16 divided by 2, and that is to be equal to 8 times the integral of course, 0 to pi over 6 cosine squared 3 theta d theta. And take note guys that cosine squared theta is to be equal to 1 plus cosine 2 theta over 2. So this is to be a trigonometric identity of this function right here. So using this identity in this part right here, this is now to be equal to, so 8, 0 to pi over 6 times 1 plus cosine 2 theta, but there is 3 theta here, so 2 times 3 theta d theta divided by 2. So once again, moving forward, so this is now to be equal to, so 8 divided by 2, so this would just go here, so times the integral of 0 to pi over 6, so 1 plus cosine 6 theta d theta. So I'm pretty sure you already know what to do in this part right here. So this is to be equal to 4 times the integral of 0 to pi over 6 d theta plus cosine 6 theta d theta. So what I did here was just to distribute this d theta here. So from that, this is now to be equal to, so 4 times the integral of d theta 0 to pi over 6 plus the integral of cosine 6 theta d theta 0 to pi over 6. By the way, this should be this one right here. So 4 times all of this, which is 4. So there, and what is to be the integral of d theta? That is simply theta. So 4 theta 0 to pi over 6 plus 4 times what is to be the integral of this one right here. That is to be equal to, so 1 over 6 sine 6 theta. 1 over 6 sine 6 theta. 0 to pi over 6, of course. So factoring out 4 here, so 4 times theta plus 1 over 6 sine 6 theta course, with the limit of 0 to pi over 6. So substitute pi over 6 here. So that is to be equal to, so 4 times pi over 6 plus 1 over 6 sine times 6 times pi over 6. So pi over 6. So this is for the upper limit. Then you must subtract the lower limit. So minus 0 plus 1 over 6 sine 6 times 0. So this is basically 0. So solving for this one right here would give you the answer of A1. So A1 is now to be equal to, so looking at the calculator to your left, so 4 times pi over 6 plus 1 over 6 times sine 6 times pi over 6. So this is to be equal to 2 over 3 pi. So 2 over 3 pi. So this is basically our answer in A1. So this is to be in unit squared. But once again, this answer right here is just to be one area here, or just to be this area right here. So for us to get the total area here, we must just multiply this area 1 by 6. So from that, the area total, so area total is now to be equal to, so area 1 times 6. So from that, area total is equal to 2/3 pi times 6. So this would give you an answer of 4 pi unit squared. So this is to be your final answer for this particular problem.